Yeah, thank you so much, Nathan. It's always a pleasure to come back to Data Science Dojo. So I'm very excited to share this presentation with you on recommender systems and its design. As Nathan already mentioned, this is the part two of the talk, and I think the part one is linked in the comments section, so you can take a look at that. If you have some questions or you want to catch up on the background, we will cover background in this talk. So if you missed out on the part one, then we'll get some of that going here as well. So my name is Karthik Mohan, and I will be talking to you about recommender systems and its design. Let me just move this out of the way. So let's get started. So a little bit about myself. I did my PhD in electrical engineering at UW here in Seattle. And then I worked at Amazon, and at Amazon, I got to work on a variety of problems, including recommender systems and anomaly detection, to name a few. So that's where I, got my brush with recommender systems at industry level. And then I worked at Meta on a completely different set of projects, mostly related to natural language processing and natural language generation. As we know, generative AI is a very popular topic these days, but that's not the focus of our talk today. And then I took a sabbatical and I was teaching courses at UW Seattle. I'm still affiliated as a professor at UW as a part-time commitment. And then after the sabbatical, I joined Chewy, which is a pet company, as a staff scientist, where I currently work as well. So that's a bit of a background about me, just to fill you in on my prior experience. And now we'll get started with today's talk. So today's talk I've kind of categorized into four buckets. One is more of introduction motivation. It's always good to have motivation to know why do we care about recommender systems and what are some examples, a real world example. So we will key into that in the first section. And the second section is more of a technical background, just diving a little bit deeper into the models that we've already gone through in part one, but we'll keep it short. And then the third and fourth segments of today's talk are the real topics for today, which is recommender system design and architecture, and some popular recommender system scalable systems that get used in the industry these days. Okay, so let's start with part one. A classic motivation for recommendation systems is Amazon. If you look at any Amazon page, you will see that it is carousel based. So carousels are these horizontal things that you can keep scrolling on, each of which might have a title. For instance, here you have add more to your cart, or recommended for you, or pick up where you left off. And these things can help us add items to cart in a more relevant way, in a more personalized way. Let's go to Instacart. This is also from my Instacart app. And I use the Byte Again feature a lot. So this is Byte Again that's showing up on my app. And that's one of the carousels. The other one is You May Like. And You May Like in Instacart is related to what I bought in the past, but doesn't have to be exactly the same. It could be some new products as well that get shown. For instance, the Vita Coco coconut water, the second one, is not something I purchased, but I got recommended that. So You May Like has things that I may like, which is not necessarily what I bought in the past. Let's go to Netflix. So Netflix also does recommendations in a carousel style. This is again my own Netflix page from some time in the past. You can see the first category is popular on Netflix, but this is popular on Netflix personalized to me, because popular on Netflix personalized to you would look different, right? And then there's personalized trends. What's trending right now? Again, what's trending right now is personalized to me. You can see there are some movies or series in here that are not even in English language, because I watch multiple. I'm multilingual, so I get recommendations from multiple languages. So that's what we see in trending now as well. And then a personalized genre, which is futuristic sci-fi, that shows up right at the top. And I'm into sci-fi, so this is making a lot of sense to me, the way it's set up on Netflix. Right. LinkedIn recommendations, again, we're all on LinkedIn, and we like to just go to the LinkedIn page and see what's coming up. I like to scroll. It's nice. I learn a lot. And here's an example of something I saw in the last few months on my feed, where this post is about ChatGPT. And there was someone in my network who commented on a post of a person who's third in connection to me. So this person is not related to me, but they are third in connection. But someone in my network commented on that post, and hence it got recommended to me, right? So it's a similar user recommendation. There is someone who's in my network and who saw something and they recommended. But it's not just that, it's also relevant content. So ChatGPT and AI are things that I keep tab on. And so this post in LinkedIn is relevant to me as well. So it's a combination of similar user and a relevant content. Okay, so now that we've gone through some motivating examples in recommender systems, you can already guess why do we care about recommender systems and why is recommender systems useful in industry? Well, if you look at Amazon, Netflix, or Instacart, any of these companies that sell a lot of products, they might have billions of products, right? And if you want to keep browsing through them, searching through them, it's very time consuming. So recommender systems can help customers save time. So that's one of the big ones why companies invest in recommender systems, is to help customers save time and purchase more products. And also surface products that are relevant. Among all the billion options or the million options that we have out there, only a subset of them might be relevant to me. And if the company can surface it, then it makes my life easier, and it's a win-win situation. It's also personalized. So if you look at any genre on Netflix, for example, if you look at sci-fi genre, your sci-fi genre, the rows, the movies that are listed in there would look completely different from mine because it's personalized. So even though the genre is same, the recommendations are different. It's personalized. And coverage. This is again connected to surfacing products. There could be so many products that are available that might be relevant to my interests, but it's hard to surface unless there is some kind of a recommender system that's covering for all the variety that's available out there. So companies also invest in recommender systems so that they can surface more diverse products to customers and increase the sales of different categories of products, right? So coverage is also an important reason why companies invest in recommender systems. So the lay of the land, part 1 and part 2, I took the talk and kind of broke it up into part 1 and part 2. And these are the things I wanted to cover in both these part 1 and 2. Examples and motivation, deep dive into collaborative filtering, design principles, architecture for recommender system design, metrics for recommender systems, and recommender systems at top tech. So in part 1, we covered 3 of these, which is listed on the left. And in part 2, which is this talk, we focus more on design principles and some design architecture and scalable recommender system design as well. So that's going to be more of our focus in this part. So before moving into the second segment of this talk, I'll pause to see if we have any questions.
So we do have one. Well, I guess there are 2 comments, but one is in the form of a question. Jorge is asking, how do you see the opportunity to implement recommender systems or recommendation systems GPT-based?
Oh, GPT-based recommender systems. I believe companies might already be starting to look into it. I believe it's a big opportunity, but then again, GPT-based models are based on transformers, and transformers are something that have already been used in recommender systems. So it's not going to be a big jump to go to GPT for recommender systems. But again, with GPT, we need to still do a lot of testing, extensive testing. But yeah, I think if there are interfaces, especially when you have a chatbot style interface where you can ask for things and then you get recommended, that's where GPT will be even more helpful versus like a traditional static page where you get recommendations.
Okay, perfect. Then we can go on and continue.
Okay. So the second segment of today's talk is going to be a recap of recommender systems that we covered in part 1. I'll focus on the most important ones that are useful for today's talk. So the big picture is on the types of recommender systems, right? Like we spoke about, you can have personalized recommendations and you can have unpersonalized recommendations. So unpersonalized is easy. Usually it's like popular recommendations or sponsored products, right? So there are companies or products that want them to be surfaced and they pay for it. So that's sponsored products. And popular recommendations, well, these just have a lot of sales. These movies get watched a lot, but they may not necessarily be personalized to you. They're just popular, right? So these are unpersonalized recommendations. So that's easy. Personalized recommendations is going to be the focus of this talk, right? And so here we have like three different models that are very, very helpful to know. So one is collaborative filtering, which uses user behavior, customer behavior. The second is content-based filtering that uses content of products, of movies, of things that companies want to sell, use the actual content information in some way, shape, or form to inform the recommendations. So that's content-based filtering. And the third one is hybrid models, which use both customer behavior and also content to inform recommendations. So you get the best of both worlds, right? So let's take a look at collaborative filtering to begin with. This is one of my favorite topics, and this was also the context for the Netflix $1 million prize that happened a decade back, where multiple teams were competing to see if they can take a crack at Netflix data set, where Netflix had like a set of users or customers and movies, and they had partial ratings for every movie from a user, right? So not all movies were rated by users, and not all users rated every movie, right? So there was like a lot of missing ratings, and the goal was to predict the missing ratings, which was on the scale of 1 to 5. And the metric that was used was RMSE, right? And so they had a leaderboard going on this, and you can see the RMSEs listed out. The lower the RMSE, the better. So you can see the top team had a RMSE of 0.85 on the test data set. And it was a almost 10% improvement over a baseline model that Netflix had going at that time. So and the top team got $1 million. So that was the Netflix $1 million prize. And most of these teams on the leaderboard that we see here use collaborative filtering in some way, shape, or form, right? So collaborative filtering, as a way of example, I just use 5 users and 5 movies here as an example. So let's say we had 5 users: Anaga, Sairam, Karthik, Naval, Dipanshu, and then 5 movies: Avatar, Arrival, When Harry Met Sally, Before Sunrise, and Minions. And let's say we have partial ratings. Instead of 1 to 5, you can have implicit ratings up or down, right? So up means you like this, and down means you don't like this movie. A lot of times for products that are sold on Amazon or movies, we may or may not get explicit ratings, especially for movies on Netflix, for instance, or videos that you watch on YouTube. You have to infer the rating. So those are called implicit ratings because you have to infer it. The data is not readily available. But let's say you either infer it or you have it explicitly available, but we'll just use thumbs up for I like it and thumbs down for I don't like it. So you can see that this matrix between users and movies is partially filled. And the goal of collaborative filtering is to completely fill it. So wherever we have question marks, fill it in with thumbs up or thumbs down in a way that makes the most sense and in a way that minimizes the root mean square error, the metric that we saw on the previous slide, right? So, and then if we did fill it in, we would have something like this, right? So here's where you can say, well, maybe Karthik, which is myself, is similar to Anagha. So maybe that's why I fill in thumbs up for Arrival for myself, right? And a thumbs down for Before Sunrise for myself, because I'm similar to Anagha. But collaborative filtering can be much more complex than this. It doesn't have to tag on to one user. You can tag on to multiple users. And also movies can tag on to each other. So it's a very complex process. But it can be formulated through an algorithm like matrix factorization or matrix completion, which is usually used to fill in this matrix, right? And hence do collaborative filtering. But the key idea is that we are tapping into user behavior of ratings to inform us on predictions and recommendations. So we may not necessarily be using content of movies or understanding of the user to make these predictions, right? So behavioral data informs collaborative filtering. And like I said, you can use matrix completion for this. So your matrix with missing ratings, and then you have a matrix for users, the red matrix, and then you have a matrix for movies, which is the green matrix. And then let's say we have a user, Amy, and we have a movie, Arrival, and I want to know if Amy likes Arrival. Then I take the user factor for Amy, which is highlighted in yellow, and I take the movie factor for Arrival, which is highlighted in pink, and then I take a dot product, and I get a score. So that score is some float, right? So here it's 0.9, it's positive. So if it's positive, usually it means that you like it. If it's negative, you don't like it. So here I would say, well, the model predicts that Amy likes Arrival. But here, you might ask, how do you actually learn this red matrix and green matrix, right? So that's where the engine behind collaborative filtering comes into play. That's where we actually optimize a loss function and optimize for an error. So this red and green matrix is completely learned from the data. So whatever data you actually know, you learn it from there, and then you make predictions. So that's collaborative filtering. One issue with collaborative filtering is if you have a new movie that comes up, let's say Men in Black, the latest Men in Black just came out, and we don't have any ratings for them. No one's watched Men in Black. It's a brand new movie. How do I recommend Men in Black, the new version of Men in Black, to any customer or any user, right? So this is what is called a cold start problem. So when you have a new user or a new movie, how do you make recommendations? That's a cold start problem. So this is where, instead of collaborative filtering, content-based filtering can help. So what's content-based filtering? So let's take an example. Let's take me, Karthik. I have watched the movie Arrival. Arrival is a sci-fi movie, right? It's futuristic sci-fi. And in terms of content, Arrival is the same genre as Men in Black, right? So if I can understand or decipher based on the content or like the description or the tags that we have for these movies, that these two movies are kind of similar, then because I watched Arrival and I liked it, I may want to recommend Men in Black to myself, right? So the engine may want to recommend it. So that's content-based filtering. This is something collaborative filtering would not be able to do because there's not enough user behavior or ratings for this movie. So content-based filtering is able to fill in the gaps, especially with cold start issues. And content-based filtering uses something called embeddings. You might have encountered this term before. We discussed in part one of the talk what embeddings are, and we went in a little bit of detail. I'll not go too much in here, but embeddings are a concise way to represent content, for example, movies or products, so that you can compare them. You can say if embeddings are close to each other, they're similar, the movies are similar. The embeddings are farther away from each other, like for example, Minions and When Harry Met Sally, they have kind of a larger angle in between them. So the cosine similarity is smaller, then they are dissimilar. So embeddings can help us understand or help algorithms understand how to compare movies, right? And they don't have to be in 2 dimensions. This was just a toy example. They usually are in much higher dimensions, like 128 dimensions or 256 dimensions. And they might have some latent dimensions or understanding of what each of these floats in the embeddings represent, right? So we don't know that a priori, but after the fact, we might say, okay, this dimension represents comedy and romance, or this dimension represents thriller and adventure, and so on and so forth. So after we have learned embeddings from the data, we can infer what each dimension of the embeddings mean for the sake of interpretation, right? But that's something that's usually done after the fact. So embeddings are very, very useful. You might have encountered it before, and it's key to content-based filtering. Okay, so let me just, now that we've kind of quickly done a recap on collaborative filtering and content-based filtering, let's just contrast the two approaches, then, kind of close on this. So collaborative filtering, the pros of this approach is it's fast to train and fast to do inference because you just have to take a dot product. So inference time is quick and can recommend a variety of products, right? So it doesn't have to be related to what I watched. It can be very different. I could have watched Avatar and I get recommended Minions because there are other users like me who watch a variety of things. It doesn't have to be restricted to a genre. So there can be variety in the recommendations, and it takes in behavioral signals, right? So that's the pros. The cons, it cannot handle cold start users or products, right? Like we saw. And it doesn't use content signals. Content-based filtering, the pros, very good with cold start recommendations, and it can recommend content similar to a given product or video. So you might have seen this on Netflix or Amazon or other pages where because you purchased a product or because you watched a movie, you get recommended other set of movies or other set of products to purchase, right? So, and you will see title that says, recommending this because you watched this movie. So that's content-based filtering. And so you can do things like that using content-based filtering. The cons, it's slower for training and inference because you have to learn these embeddings, and there may be pairings between users, and there may be pairwise interactions between users and products that can slow down training and also inference. It doesn't take in user behavioral signals. It only is based on content signals, and therefore there's less coverage because you're always looking at products similar to what I have already purchased or already viewed or watched. So that's the kind of the cons of content-based filtering. Okay, so that's a recap of some of the things that are essential for the next segment of the talk. So we'll be moving into segment 3, but I'll just pause to see if you have any questions.
Yeah, so first, I want to address, I think it's Truce or Trucy. Truce, we're going to keep your question for the end. I think that's a better question for the end of this. You might actually get it answered while we're going through the presentation, so we're going to save that one. This one's from JC. How do you account for user preferences over time? And how do we assess if accounting for time makes a difference in improving predictions?
That's a very good point. So there are different strategies. One strategy that I've personally used in the past is to train on the past, but predict for the recent past, like recent 3 months. So you take your training data and then you break it up. Let's say last 12 months, you break it up into 9 months and 3 months. You train on 9 and predict on 3. So because you're predicting on 3, you're going to get metrics on the last 3 months. Though that's like the recent behavior, the recent trends. So you can see if your algorithm is still able to, or your model is still able to bias towards getting the recent trends right. The other one, so that's setting up, training in a way that can promote emphasis on a recent behavior, right? And this is especially true for, let's say, if you're shopping on Amazon fashion changes like that. So you cannot use 1-year-old behavior to inform what the fashion trends are right now. So you have to be current. So it's pretty important for that. The same thing with trending videos, TikTok, YouTube Shorts. Again, you cannot look at something that I've watched 1 year back and say, well, I will share this with you because it's not trending. It's not going to be a good recommendation. The second thing you can do is to incorporate features in the model that get weighted by recency, right? The more recent impression is, the more weight it gets. The farther away the impression is, the less weight it gets in your feature, the way you've set up the features for the user or the content, right? And that way you can also incorporate in the model. So the first one that I described is a way to train, but also you can test, right? So you also asked about testing, so you can also test. The second one is a modeling change that can account for or bias the model towards more recent impressions. Yeah. So I hope that that's an answer for your question.
And then next question before we move on. Why don't you use public and complementary sources of enrich collaborative part with magazines or something similar?
I didn't get that question. So is the question why not scrape public data to build recommendation models? Is that the
Yes, or
question?
why don't you use something that's public or a complementary source of data?
So if you look at the recent trend in AI and generative AI and things like that, that's what's happening, right? So almost everyone is using pre-trained models and then fine-tuning it on their data set. And when we look at content-based filtering in the context of recommender systems, content is language data, right? So natural language. So transformers are a natural fit for that, and transformers are pre-trained, so that'll be pre-trained on a very huge corpus, like you were mentioning. But that's but for your company specific recommendations, you still need to fine-tune. So the fine-tuning part still needs to be done on private data, which is company specific. So that would still have to be done. But yeah, you can, if using transformers or other pre-trained models, even if you have images in your products, like videos or thumbnails for movies or images for products, and you want to extract image features, again, you have pre-trained models for images that can be leveraged, and then also fine-tune on company-specific impressions data. So yeah, totally, we can do that.
And then I lied. This will be the last question before we move on. Is it possible to use both filtering strategies together? And like, if so, would that give you a better recommendation or anything like that?
Yes and yes. So we're going to discuss that in the next segment of this talk.
All right. Well, then let's go ahead and move on.
Yeah. All right. So the next segment of the talk is on recommender system design and architecture. So we've kind of, so far we've kind of established some ground, like, okay, these are the basic models: collaborative filtering, content-based filtering, and what are some things to keep in mind. We've kind of discussed that, pros and cons. So these are kind of like building blocks that we will now use into full-blown recommender system design and architecture, right? So for that, let's look at design considerations. What do companies care about when it comes to recommender systems? Like, what are your North Star, like goals or metrics that we want to hit as far as design is concerned, right? So here are some things I've listed, and this is not exhaustive by any means. There could be many more that I missed here, but these are definitely some of the important ones that companies would care about as far as recommendation system is concerned. So the first is relevance, right? If your recommendation is not relevant to me, then why are you even building a recommender system? So relevance is very important, and we'll talk about how we measure it. Second is cold start. There are new products coming out every day on Amazon or Instacart or any other retail site. There are new movies coming out on Netflix, new web series coming on Netflix. If Netflix doesn't surface it, then I'm not going to watch it, and if I don't watch it, it's not going to get viewed, and then so on and so forth. So cold start recommendation is important. So is the recommender system addressing that? Diversity. So diversity is again related to coverage. Not just cold start, but also even popular ones that don't necessarily fit in my purchase behavior or my viewing behavior. Maybe I don't watch comedy, but there's a really popular comedy series that just came out, and I might be interested in that, right? So that is diversity as far as I'm concerned. Even though that's not cold start, it's diversity, right? So that's a difference. So diversity is something that also companies care about. Like, TikTok, you want to show different things, make more videos viral, blah, blah, blah. So there could be many considerations for diversity that show up in, different places where things get recommended, right? Freshness, like we spoke about fashion, things, recommendations have to be fresh for certain categories, right? Fashion is one example of that. Trending videos, again, it has to be fresh, things have to be recent. Latency is an important design consideration for recommender systems, because you cannot sometimes just store recommendations for a user. It is just not feasible, right? If you're dealing with billions of movies and millions of users, you cannot be storing a bunch of recommendations for every user, because you may want to sort it, filter it, re-rank it, do a bunch of things, or it's just not feasible. The infrastructure doesn't support it. So then you have to do inference in real time, and that will incur latency. And so we have to look at latency considerations as well. Fairness, this is a new one. Fairness is if there are two products or two movies on the market, is one getting recommended more than the other for no particular reason, then we're not being fair to those set of movies. Or if one user is getting better recommendations than another user for whatever reason, then we're not doing a good job. So fairness is more about that, either from the user's perspective or from the product side. And then scalability, this is one of the biggest ones. So we'll talk about a template here in this talk on scalable system design for recommender systems. But when you go from 100,000 movies to 1 million movies to 10 million movies to billion movies, then the scaling changes, the design also changes, right? So these are some design considerations. So let's take a look at one at a time. Relevance, right? So going back to the Netflix example we had earlier, I like sci-fi movies as a person. Like I really like sci-fi movies. So I see sci-fi recommendations as the first genre on my Netflix page. Makes perfect sense. It's relevant, right? Now, how do I measure relevance, right? So there are some metrics that are used to measure goodness of a model as far as relevance is concerned. One is precision, one is recall. And in recommendations, you see this precision at K, or average precision at K, used a lot. So this K is like the context window that you have to show recommendations. So we'll talk about it. Let's look at an example. So using an example of purchases on a retail site like Amazon, right? Let's say the top row, purchases, is my purchase history, right? Like I have just purchased this in the last 1 week, or I would have purchased something similar in the last 1 week. And then the second row is what the model's recommendations are. So the model is trying to recommend things that are close to what I purchased as a way of showing that it's actually capturing what I like, right? So I want to match the recommendations with my most recent purchases to show that, yeah, so what I'm recommending is what I would have purchased. So that's good. So here, if you look at precision at 4, right? I am actually limiting myself to the top 4 recommendations. I'm not looking at all the recommendations I make. Why? Because sometimes you're using an app, you're looking at recommendations on an app, you're scrolling through Instacart, or even on a web page, you might have only like a context window of 10 or 5, right? So it's good to know in that 5 context window context window of size 5, is the model getting the right recommendations, right? Is it showing something random or is it actually showing something relevant? So limiting it to a context window and using precision in that helps me understand how well the model is doing. So let's look at precision at 4 here. So highlighted in pink in the recommendations tab are the ones the model got right, because you can see vitamin water is present in the purchases and it got recommended at position number 1 and position number 4. But position 2 and 3, it didn't get it right because Ziploc and the cereals Cascadia Farms wasn't in the purchases. So we would say that it didn't get it right there. So now the precision at 4 is 2 divided by 4 because 4 is the context window. You got 2 right, so that's 0.5. Now, what happens if I swap vitamin water at position 4 here with dark chocolate mocha almond as a recommendation? You can see this this kind bar is not part of the purchases, right? So that means the number of recommendations I got right in a context window of 4 is 1. So the precision at 4 goes down from 0.5 to 0.25. So you can see this is able to capture if you're getting things right in a context window. And we spoke about this in part 1 of the talk too. You can refine this metric to also look at ordering, like ranking. So recommendations ranking metrics will also use something like average precision. So we will not go into that, but you get a drift. Higher the precision at K, the better your recommendations are, right? So that's one way to measure relevance offline. Let's look at diversity. So diversity is very important, like we spoke about, and diversity in session is really useful. For instance, you're shopping on Amazon or you're shopping on Instacart, and you added Fiber One as the cereals to the cart, right? Now that I've added cereals, would you recommend cereals again, or would you recommend something else, right? So in this example, you might recommend coffee instead of cereals because you already added cereals to cart. So it doesn't make sense to show the same thing when you already added it to the cart. So that's where diversity also plays a role. So how do we measure diversity, right? Here, you can see that the volume, which is represented by this parallelogram of adding Cheerios to the cart, is less than the volume of adding Gevalia coffee to the cart, right? So, and a measure of diversity mathematically is the volume, and volume is captured by determinant of the similarity matrix. So determinant of similarity matrix is a metric to measure diversity, and people have optimized for it in the industry or in the literature as well. So that's diversity, right? Now let's look at latency. We looked at a matrix factorization. Sorry, one second. So we looked at matrix factorization as a collaborative filtering model for recommendation systems, right? So here Amy gets recommended arrival because the score is 0.9, which is positive, which is significant, and hence we'd say Amy likes arrival. So what's the latency of this? If we can cache the embeddings for the users, which is Amy and other users, and for movies, which is arrival and other movies, then when Amy shows up online, we already have Amy's embedding in cache. We can retrieve it, and then we can have a candidate set of movies to pick from. Maybe we have 1,000 movies. We've already kind of filtered out, and we have 1,000 movies. Then we need to take 1,000 dot products and then sort it and then pick the highest top 5 that are the top scoring ones, and then recommend those for Amy as recommendations, right? So because we're able to cache in this particular example, we might be saving on latency. If we didn't cache, So for collaborative filtering, you would be caching, so you would not be doing much anything else. But we'll look at models where it's not easy to cache, and then you incur extra latency. You can also maybe just store recommendations for every user. So when the user shows up, you just show them that recommendations. And that can work in certain contexts, but if you look at session recommendations like we just saw earlier, or we're looking at large scale recommendations, then caching the recommendations becomes infeasible, right? And so you would have to use embeddings and then cache them and then incur latency there as well. So yeah, so there are some tricks that can help with latency, but we'll look more into this as well. Okay, the next one, next big one I want to talk about is scalability, and this is a really big one. So let's look at the context of movies, right? So you can have 100,000 movies or 1 million movies or 10 million movies or 1 billion movies as candidates to recommend from. When we look at the segment of 100,000 movies, it's easy to train on 100,000 movies. It's easy to predict, and you might even have very low latency because a simple algorithm like collaborative filtering would work. But as soon as you start going towards billion scale, then the training process becomes very complex and convoluted, and you also incur higher latency during prediction time. And you might not even have the latency budget to push a single neural network model as the model for making predictions. So neural networks may not scale as is due to memory and compute constraints when you increase the scale of the data set, right? And so you may need a multi-stage approach, and we'll talk about this. A popular architecture, and someone asked this earlier, can we combine collaborative filtering and content-based filtering? And here's two-tower architecture that does just that. So we'll use two-tower architecture as our starting point towards building a scalable recommender system, right? So what's the two-tower architecture? So as it says here, there are two towers. So there is the user tower, and then there's the product tower. So in this particular example, you see news, but you can replace news with movies. You can replace movies with retail products. You can replace it with anything else. So essentially, there's a user tower or a customer tower, and there's a product tower, right? What is this tower doing? It's getting refined features, maybe through neural networks or through layers, so that we can use those features as embeddings and then take dot products, right? But it doesn't stop there. In two-tower, you can also have pairwise interactions between users and products. So you're not just taking a dot product between user embeddings and product embeddings, like in collaborative filtering. You might also have pairwise interactions, which is where we incur extra latency. Like as we, in contrast to collaborative filtering, this is where we incur extra latency when using the two-tower architecture. But it's a hybrid model, and it has its pros, right? It does collaborative filtering because it uses user behavior. If a user likes a news article or a movie, you get a positive rating. If you don't, you get a negative rating, and we're using that data. So it does do collaborative filtering. It also does content-based filtering because you can start with a representation, a raw representation of a news article or a product or a movie. Like you can have a bag of words model and then build from there, or you can use a pre-trained model. Let's say we have language data. We can pass it through a transformer model and get transformer embeddings as a starting point for a news article or for a product or for a movie, right? So that enables content-based filtering because you can also take care of cold start, right? So in terms of relevance, yeah, this two-tower architecture supports relevance, right? Because we are using user behavior and we're also using content data. We can do caching to some extent. We can do caching until the point where the pairwise interactions start, right? So we can do some level of caching here, and that can reduce latency. We can do cold start recommendations using content-based features. What about diversity? Two-tower architecture as such may not promote diversity or support diversity, but we can add a diversity filter or a re-ranker on top of this model, right? So we can add a layer after this to filter for diversity. And same thing for fairness. We don't know if this model is going to be fair because models are as good as the data. And you might have seen this from your past experience that if there is bias in the data, it's going to show up as bias in the model as well. So fairness is a separate topic, and we may have to still do separate evaluations to see if there's any major fairness issue that this tutor architecture is incurring, right? So we'll use the tutor as a starting point to build a scalable multi-stage recommender system, or talk about it in the next segment. But before that, I want to see if we have any questions, and I'll pause here.
Oh, we do. And I am going to start you off with a question from Grace. What's the usual criteria for precision? And an example is like in a movie recommender system.
Criteria for precision? So I is that, are you asking for threshold? Are you asking for how do we measure precision?
Grace, if you could clarify that for me in the chat, I'd appreciate it, and maybe we can circle back once we have that clarity. We had a question, and there was a question answered in the chat, but I want to make sure everybody hears it. Can you redefine what you mean by cold start?
So cold start is like we have a cold customer, or we have a cold product, which is the customer is new, right? So it's a cold start customer, or the product is new, it just got launched, a movie just got released, so there's a new product on the market and we don't have enough data on it, so it's a cold start, right? It's not a warm start. I don't have a hot start on it, so it's a cold start. So that's what we mean by cold start. So there's not enough data that I can use features to do good recommendations on. I would have to rely on content features to make recommendations. I don't have behavioral data on it, so that's cold start.
Okay, and then another clarifying question: is K equals similar to something like the K nearest neighbors algorithm?
Yeah, so the K nearest neighbor algorithm is yeah. I mean, you can say that the K is just a hyperparameter, right? So the K can be 5 or 10. In that sense, it is similar. K nearest neighbor is like saying, find me the K nearest neighbors to an image or a data point. So here, the K, the way we are getting the top K recommendations is kind of similar, because we are scoring different products or different movies. And once we score them, we sort it and we take the top 5 or top K. That top K is kind of the nearest or the most similar, you can say. So in that sense, it's kind of the same context, but these are different algorithms, right? We're not talking about the exact same algorithm here.
Mm-hmm.
But the K is used in a similar way. Yeah.
Okay, perfect. And then going back to that question about precision, Grace is wondering about the threshold for precision. Like, how accurate do we expect the recommender system to get?
Yeah, that's a good one. So, there is something called the area AUC curve, which is like the plot between false positive and true positive. And then you see, you change the threshold at which you say something, you want to recommend a product to a user or not, right? So if you change the threshold, let's say the threshold is 0.5. If the score is greater than 0.5, like, we saw that example where Amy likes Arrival because the score is 0.9. So maybe the threshold there was 0. If I shift the threshold to 0.5, I would still recommend this Arrival to Amy. But if someone else had a score of 0.4, we would not recommend, right? So the threshold influences the precision and recall, right? So as you change the threshold, the precision might increase and the recall drops. Or if you decrease the threshold, the precision decreases and the recall increases. So that's something that's also a design choice. So a lot of times people optimize for recall or precision, right? So if you optimize for recall, you definitely want to get the purchases or movies right, but you might make false recommendations. Okay, but if you optimize for precision, you're being very, very picky on what you recommend, but you miss out on a whole lot of other things that the user would have liked because you optimize for precision. So it's a design choice to see where we want to fall, and the threshold that you mentioned does play an important role there, right? So it's entirely dependent on the problem that we're looking at, or on the specific project that you're working on, right?
Okay, and then final question before we move on. Um, is matrix completion the main algorithm to implement recommender systems, or are there other common algorithms out there?
Yeah, so matrix completion is very popular for collaborative filtering, but these days the tutor architecture kind of subsumes matrix completion. It's like a more advanced version of that because it also does content-based filtering. So we started out there so as to explain it, but these days mostly, in many contexts, people don't just use matrix completion. They would use it as a module or as a part of a bigger architecture like the tutor architecture. And that would also be part of a bigger architecture that we'll be talking in the next segment. So it's like these are all different modules that go into a bigger one, and then you might even expand that out depending on your needs.
Okay, perfect. And let's save the rest of questions for the end, and let's go ahead and continue.
Okay. So we're getting to the last segment of today's talk, so which is at an industry scale, right? At a billion scale, when we have a lot of products to recommend from, how does a recommender system design look like? Okay, so we'll start with the tutor architecture, which has a user tower, product tower, and user product interactions. So the good news is that this is a hybrid model. It does collaborative filtering and content-based filtering. It can surface relevant recommendations. It can account for diversity once you add a diversity re-ranker. It can take care of cold start. So this is all the good things about the tutor architecture. But the not so good news is that it doesn't scale even with caching. And the reason is you might have pairwise interactions, which you cannot cache. You can only cache until that point, and then you'll still have to go through the pairwise interactions in real time to make a recommendation and incur latency, right? So for this reason, we need a multi-stage approach, and this is typically what the top tech companies use as a multi-stage approach to recommender systems. So I'm using a template here, but this template applies to many different recommendation engines used by top companies, right? So this flavors of this design is used by YouTube. Pinterest, incidentally, uses more than one. Like their real-time recommender uses graph recommendations. So they have more than one recommender system model. Twitter and Instagram as well. So the idea here is to, you might start with billions of candidates, but kind of filter it out using a very simple heuristic or a simple model to thousands, and then use a more complicated model to reduce thousands of candidates to hundreds, and then re-rank it to generate dozens. So this is like the funnel that you go through from billions to thousands to hundreds to dozens. And that's a multi-stage approach. So use simpler heuristics, faster models, less accurate models, but they give you good, reasonable candidates from which you will cherry pick, and use more complex models in the later stage to cherry pick the ones that are most relevant to the user or meet your criteria, right? So that's the whole idea of this multi-stage scalable recommender system design. So let's look at candidate generation. Usually a simple heuristic, maybe popularity is one. You can use popularity filters to filter out some of this. You can also use simple collaborative filtering like matrix completion model. Like someone asked matrix completion, can we use it? Well, this is a good place to use it, and filter it down to thousands, right? These thousands may not all be very relevant, but they will be relevant ones in them. So you'll have to cherry pick and use a more complicated model. And then in the second stage, which is a scoring stage of these, you've generated 1,000 candidates, filtered billions to thousands. Now let's score them. For that, you might use a tutor model that we just spoke about. So now you see tutor is a component of the scalable recommender system design, right? But this is not where we stop. And one thing I should mention is that here we may not use any video, using the example of videos, right? We may not use any content features or video features. But in the second stage, we actually tap into a video feature store and extract features for videos and then use that as input to this model, which would be a tutor model, for instance. And now that we've come down to hundreds, we would maybe re-rank this because we care about diversity. Like we spoke about diversity, we care about fairness, we care about popularity, we care about trending. So you see that many, most of the recommendation pages like YouTube or Instagram or Instacart or TikTok have different categories, or Netflix, for instance. Netflix is a good example. Have different channels for recommendations, right? There may be a popular channel, there may be a trending channel. Like Netflix has a popular channel, it has a trending channel, and then it has a genre, your favorite genre. So you have different channels. So you may want to re-rank to account for that, right? So this suggests that why not break up the re-ranking into different segments? So now we have a segment for trending, now we have a segment for popularity, now we have a segment for personalized to you. And these may be optimized or re-ranked in different ways. So you start with hundreds, but you kind of re-rank it based on you want to focus on trending, or you want to focus on popular, or you want to focus on something else, right? So this is one way to take care of the multi-channel recommendations, right? Building on top of this, we might want to move this one step ahead in this fashion. So instead of re-ranking, instead of taking the hundreds and re-ranking, why not optimize for trending early on? Why not optimize for popular videos early on? So from the tutor model, whatever outputs we get, we ask the tutor model to specialize for trending, or specialize for popular, or specialize for something else. And this way you can get multi-channel recommendations from a single framework, right? So you start with a big a multi-stage approach, but towards the end you start to branch out for multi-channel. So this is a multi-channel scalable design. And then the next thing to think about is real-time recommendations. And this is something that's very important. One example of real-time recommendations is in-session recommendations, right? So you are in session. Maybe you just finished watching Arrival. Okay, I just finished watching Arrival, or I just finished watching a web series. What's the next thing to recommend? I'm still in session. I'm still live, right? Knowing this, my recommendations will change, right? I cannot just show the same static recommendations. Now that I watch this in session, I want to change the recommendation. So this is session recommendations. Using this information, we change the recommendations that we surface, right? So we may have a different model or a different re-ranker to take care of session recommendations. And this is, again, this is a very interesting example. For movies or for videos, maybe I am like in a specific genre right now. Maybe I'm looking at thrillers and I want to keep watching thrillers, right? So maybe I want to recommend other thriller movies or web series as the next thing to watch in session. But when you look at products, that's not true. We look at an example. If I've already added cereals to my cart and I'm in session, don't recommend cereals, recommend something else, recommend coffee. So depending on the context, the in-session recommendation model may look different for different, different contexts. So that's something to think about and keep in mind. Typically companies, as they start scaling, they'll start adding different modules depending on the needs, depending on the requirements, depending on the metrics, depending on where the revenue is. And so you'll see the design get more and more and more complicated, especially when we get to real-time recommendations, it can be even more complicated. And we haven't gone into the system design aspect of this. We have stuck to machine learning design here, just to kind of not go too much into the details, but you can imagine that also gets more complicated, the more complicated the machine learning design here. Yeah, so I think I'll just go into some of the last part of this last segment, which is evaluating the design. So once you have a design for recommended systems, how do you evaluate it, right? How do you know you have a good design, right? Okay, we have this really fancy design, right? It has multi-stage and everything. How do you know it works, right? So that's where we have to come up with offline metrics to benchmark our model or our design on. And as we know, we care about relevance, we care about diversity, we care about cold start. So we'll have metrics for each of these and make sure our model is doing well on each of these, right? You can benchmark on an offline data set. And maybe you have more offline metrics as well. And then you have business metrics. Well, offline metrics is something that we have control on. I can control relevance, or I can measure relevance, but I may not be able to measure revenue until I launch my design, right? Until my recommender system is live, I don't really know how much revenue it's going to generate. So that's the business side of things. That's the business metrics. So revenue, if it's videos, view time, click-through rate, if it's products, number of products viewed or purchased, in a given session. These are some business metrics that companies would care about. So you can see the offline metrics look a little bit different from the business metrics, right? For instance, if I optimize for diversity, I show a variety of products or a variety of movies to users. That doesn't necessarily translate into revenue, right? Business might care about revenue, but you are optimizing for diversity. So there could be a gap, right? It can help, but it's not a guarantee. So this is called the offline online gap. We benchmark on offline data sets, we test on offline data sets, but when we go online, we find it's not exactly matching up. We're not getting the results that we care about. So companies also focus on bridging the offline online gap between the business metrics and offline metrics. So how do we bridge the offline online gap? One is to have held out test set. That's different from your train, validation, and test set. You have a held out test set that's more extensive and benchmark on it. And it might have use cases that the model's never seen before, and see if you do well on that. You can do internal testing, dogfooding before you launch your recommender system. And obviously, we want to do A/B testing. That's obvious. You want to A/B test, if you can, definitely A/B test, and make sure that when you actually launch, you're going to increase your business metrics that you care about. But even after launch, you'll still have to monitor production metrics, right? Make sure your model still keeps doing well on after launch, that there is no data drift that's impacting your model. The model is still doing well. So you might want to collect production data and then keep doing offline evaluation to make sure your metrics are in a good place. So some of these things can help bridge the offline online gap and make sure that the recommender system that you launched, that you designed, is doing a good job before launch and after launch. So that's the end of the talk. In summary, we looked at some motivation for recommender systems. We did a recap of recommender models, the kinds of collaborative filtering, content-based filtering, hybrid models. We did a recap on that. We looked at some design principles that are important for recommender systems, and that any recommender system, you need to think about these design principles and make sure you check off at least a few of these boxes, like relevance, diversity, etc., for your recommender system, and be able to measure it and show that you're actually doing well. So that's part of the design as well. We looked at the two-tier architecture as a very good starting point and as a module that can be used in a bigger scalable recommender system design. And we looked at a template for that as well. And we looked at how we would do benchmarking and evaluation of our recommender system, both offline and online, and bridging the offline online gap. So that's about it. Thanks, everyone. And I'll pause for any questions.
Thank you so much, Karthik. So it looks like we're already past the hour mark. So you have a couple more minutes where we can try and get through as many questions as possible, and then we'll cut off maybe in 5 to 10-ish minutes.
I can stay 10 minutes or more, depending on questions. Yeah, sure.
All right. So we got Truce has this question. They're getting started with, they're kind of a beginner. They want to work on a project to build a recommender system for travelers and tourists that they can add to their portfolio. And they're curious to know, how to carry it out. Should they work on this project as a team? Can they do it individually? And do you have any recommendations for deploying the recommender system they eventually build?
So I think the first part is easy. Working in a team is always good. So if you can work in a team, work, but break down the work so you can complement each other and not put brakes on each other, right? So that's something to just teamwork is always good. And also with teamwork, you can brainstorm new ideas and you can do different things and you can break the work down. So it's always good to work in teams. With respect to starting points and deployment, there are I'm assuming this project is for a personal project, or it's a capstone project, or is it a company project? Any thoughts on that?
I believe it's a personal project.
Personal project. Okay. Personal project, it's good to, there are ways to do deployment of this. I'm assuming that you want to build a web page or something where, a user comes in and asks a question or something and they get recommended some products or, I'm assuming that's the context in which you want to do deployment. That's not too complicated. If you have a neural network recommender model, you can use Onyx or ThoughtScript to kind of package it so that it has fast inference, and you can work. You can work with one of the JavaScript and React frameworks that enable real-time inference on recommender systems. So there are some examples of that available, so you can take a look. I think Next.js, if you just search for Next.js and React for recommender systems, you'll get some references on Google, and you can follow that for deploying, building your system.
I am muted. All right. So how can, and this is back to Jorge, how can I do A/B testing? And I think this is probably a talk, a separate talk itself. How can I do A/B testing? What if they have multiple systems running at once?
Yeah, that's a good one. So at companies, people usually break down the entire customer base into different segments and make sure any given segment only has one A/B test running. So that's a way to kind of make sure that you're not having conflicting things going on. So typically there is like a MLOps segment or DevOps MLOps team that's devoted to A/B testing that makes sure the segmentation is going well. There's a dashboard for A/B testing. There's a place where you can launch A/B tests and things like that. On your own, it's difficult. But usually if you're in a setup where you have infrastructure, it's not too complicated to do A/B test. But yeah, you have to take care of a few things. And there's also statistics involved in A/B testing, right? You want to make sure that the results of A/B test are significant, statistically significant. So you want to incorporate statistics as well in your A/B test and report significance. Yeah. So those are some things that I can think of. Yeah.
Okay, perfect. And I'm going to ask you one more question because I am actually running into a blocker on my schedule. So this is from JC, a clarification question. JC says, I assume the same user entries are not grouped. Otherwise, you could get cold start if you have one set of customers in your training data and the other set of customers in your validation data.
Yeah. So we usually assume that what typically happens is if you have new customers, you have a way of dealing with recommendations for them. And once you collect enough impressions or data for new customers, you add them back to the training data set. So if a customer is present, your model has seen it, then make regular recommendations. If not, then do something else. So that's the kind of logic that you would have for cold start or a regular customer, right? But definitely want to keep piping in. If a new customer becomes old because they've been there around for some time, then add them back to the pool and then retrain. So retraining keeps happening for recommender systems. Companies usually do it on a daily basis. Sometimes like TikTok would do it on an hourly basis because they have so many viral videos coming, trending videos coming. So you want to keep retraining every hour. So there will be a training schedule in which you are able to incorporate new users, new videos, new products into the pipeline and make